thank you very much. It's a great pleasure to be part of get to be part of this celebration of Maxime and of all the great mathematics he's given to us. Okay, so I'll talk about counting curves on Calabi-Yau threefolds. So let's begin with X, smooth, projective, variety over C of dimension 3. And let's recall the various ways we know to count curves in X. So first, maybe let's fix a homology class, count curves in this class. So the first thing we might try to consider is just all smooth curves inside X. Now this is a very nice space. It has what you would usually call the virtual fundamental cycle, or said in perhaps a more pedestrian, understandable way, that's a what I call a notion of counting with multiplicity. So you think of this as analogous to the following situation. You have some manifold and a pair of submanifolds, and you'd like to count their algebraic intersection number. So that's something which we know is an object of algebraic topology, has some sort of homotopy invariant meaning. However, the way we usually like to think about it is, well, if your submanifolds are transverse, then you can just literally count the intersection points if that's dimension 0, or more generally take the fundamental class of that intersection if it's higher dimension. Now, you might be in a situation, however, where the intersection is non-transverse, but those two submanifolds still have an algebraic intersection. And this notion of counting with multiplicity, this virtual fundamental cycle, comes from some sort of intrinsic structure on the intersection which remembers this algebraic intersection number. So this space has that, and there are a few different ways of seeing that, either using analysis or using algebraic geometry. But that's not really the point of my talk. So maybe I'll skip that part. So the space is nice in this sense, but it's not nice in the sense that it's usually not compact. So to get any sort of count, we need to compactify. Define a count. Okay, and there are many ways of compactifying. So first, one might try to define Gromov-Witten invariants. So these are defined using this moduli space of stable maps introduced by Maxime. So we consider nodal compact curve C, map from C to X, which are stable in the sense that has finitely many automorphism groups. And concretely, that just means C doesn't have any unstable components which are contracted to a point. And this prime means that I want to restrict to the setting that U is non-constant on every connected component of C. So that's not really necessary. You could remove that and get equivalent invariants, but it's convenient to write down the generating functions that are going to be relevant. Okay. So the space is now.
It then became not compact because you have not model singularities.
Sorry, which?
No, but it's connected components, not irreducible components.
Oh, yeah, yeah.
On any connected.
Yeah. Yeah. Okay, so we take just the curves in class beta, and so it's also non-compact for the reason that the Euler characteristic could be arbitrarily negative. But if we add a formal variable t keep track of that, then we get these rational numbers. And I'll just remark that the rationality comes from the fact that this is not a space, but an Orby space. When we compactified, we had to include multiple covers which have automorphisms, and that has the effect of giving us only rational numbers.
Should we not use that if you fix beta, you probably will get finite many. Sorry? You get finite.
I mean, I can always have these like multiple covers with arbitrary many. No, but just I can fix the covering multiplicity to just add many branch points to get negative Euler characteristic. Maybe it will be finite, but it's not obvious.
No, given beta.
No, but so you fix the covering. I mean, the covering degree is the same, but translation you can change the Euler characteristic. So this has infinitely many things in U.
It certainly won't be compact unless I fix the other characteristic.
If you fix the number of connected components is locally constant. So if you fix the number of connected components in the arithmetic genus and the beta, then it is compact.
Yeah. Okay. So there's also Donaldson, Thomas invariants. They come from a different way of compactifying the space. So roughly speaking, for this compactification, we view the curve as a parameterization, and we allowed the domain to degenerate. So for this compactification, we're going to view C as sort of cut out by some equations and allow those equations to degenerate. So to be more precise about what that actually means is we look at closed subschemes of dimension 1. Now, I can't actually say dimension equal to 1, it's dimension less than or equal to 1. So this space includes subschemes which are support on curves and points, and those points are flying around the manifold are a little bit annoying for technical reasons. And so to find a sort of better moduli space, which is easier to analyze, Pandharipande and Thomas introduced this moduli space of stable pairs, which is a bit more complicated to define, but turns out to be easier to analyze. So now you just consider any coherent sheaf F, not only an ideal sheaf, but any coherent sheaf. Now the dimension of the support let's say F is supported in dimension 1. F, support F is pure dimension 1, and the dimension of the support of F modulo S is 0.
Sorry, what does that mean? Support of F modulo S? Not
just
the image.
In the image.
Yes.
But it could be empty, and then the dimension is minus infinity.
That's correct. Maybe I'll write less than equal to 0. So the Donaldson-Thomas invariants are integral over this space, again, the stuff in homology class beta, and now we keep track of the holomorphic Euler characteristic of that closed subscheme. That's a Laurent series, formal Laurent series in Q.
You have to define fundamental class, virtual fundamental class of this.
Yeah. So the same. Yeah. Yes. So this virtual fundamental cycle needs to extend to all of these spaces, and that's a non-trivial statement for sure. Yeah. And here we keep track of just the holomorphic Euler characteristic of F. Okay, so the point of my talk is not really to go into these precise definitions, but I just want to write them down to give a flavor for what's going to come next. So one thing to say about the Gromov-Witten invariants, they make sense for any symplectic manifold. Algebraicity is not important, and they make sense in any dimension. The significance of 3 for Gromov-Witten invariants is that the virtual dimension of the space is, remembering correctly, it's n minus 3 times the Euler characteristic plus the Chern class of X evaluated on beta. So when n equals 3, this term goes away, which is very nice. So for instance, in the Calabi-Yau case, or just a beta which is orthogonal to the first Chern class, it's dimension 0. We just get curve counts. Where on the board? I'm virtual. Virtual, yes. Virtual. Yeah. For the Donaldson-Thomas invariants, to have a perfect obstruction theory on these spaces, this notion of counting with multiplicity, that uses n equals 3. I mean, one can do things for other dimensions, of course, but that's a more complicated story. So 3 is sort of essential for this theory in this form, and this also requires algebraic or holomorphic setting. I mean, no one's figured out a good way of making sense of coherent sheaves or closed subschemes on arbitrary symplectic manifolds, as far as I'm aware. Okay, so these invariants have been calculated in many situations, far beyond what I understand, at least. And all of these calculations suggest that sort of any way you can possibly count curves in dimension 3 on smooth projective varieties are equivalent, in the sense that the generating functions are related by some change of variables. But proving this is proved to be a challenge. So one first result in that direction is by Bridgeland, who proved that Pandharipande-Thomas and Donaldson-Thomas invariants are equivalent in this sense that those generating functions are related by this. Now this is a very difficult theorem, but at least you have somewhere to start, since these 2 invariants come from the same world. Now there's another conjecture of Wallach, Nekrasov, Okounkov, and Pandharipande, which is perhaps more mysterious, which states that in this normalization, these 2 invariants are equal under this change of variables q equals minus e to the IU. I just state the simplest version. You can also state the version with cohomology insertions. So it's been checked in many cases, and I should note that when this was first, I'm stating it a little bit anachronistically. When it was first stated, Pandharipande-Thomas invariants weren't around yet. So it was stated in terms of Donaldson-Thomas invariants on the right-hand side.
But the ones are rational coefficients here and integral here, so how can this be consistent? Yeah. Because of the E, okay. Yeah, so somehow it's even the integrality of the result of doing this change of variables is already a non-trivial statement.
just that. Yeah, and also the fact that I can do the change of variables at all is a non-trivial statement, because this is an expansion around q equals 0. That's an expansion around u equals 0, which is not respected by the change of variables. So the second part, which is sort of needed to make sense of the first part, is that I guess pt is a rational function of q, and then makes sense to substitute in this change of variables expands around q equals 1. So this is known in many, many cases. I'll just write down a very small number of them. I think there must be, but I shouldn't say for sure. So it's known for local curves. This is by Bryan and Pandharipande. And who calculated the Gromov-Witten theory, and Okounkov and Pandharipande, who calculated the Donaldson-Thomas, Pandharipande-Thomas theory of local curves. Local curve is just a vector bundle of rank 2 over a curve, the total space thereof. So this is not compact. So you probably wonder what do these invariants mean in a non-compact setting. So the answer is that you look at this tautological C star action on E just given by scaling the fibers. And since the fixed locus of that action is just the cycle supported on the 0 section, and that's compact, you can make sense of equivariant invariants. So it's known in the case of toric manifolds, Malik, Oblomkov, Okounkov, and Pandharipande.
Are we assuming Calabi-Yau or not?
Sorry?
Do we have to assume Calabi-Yau or not?
No, not for, no. I assumed Calabi-Yau when I wrote down the simple thing and when I wrote down this conjecture in the simple form, but no, it's for any, no Calabi-Yau assumption, and for all insertions, in primary insertions, descendant insertions. The formulas are complicated enough already, and that's not the point, so I just wanted to state the simplest version. But yeah, for the toric case, they do all the insertions, all the descendants, fully equivariant, everything. Okay, and then the final result I want to mention is that it's known for complete intersections in the product of projective spaces by work of Pandharipande and Pixton. And what they did was they showed that they can define the degeneration of one of these to one of these and relate the invariance of this one to the one it degenerates to. So that's maybe the first result on this conjecture, which doesn't really rely entirely on just explicit computation. This is just you explicitly compute both sides, but this is sort of a more flexible sort of argument. Okay, so now we're going to start a new topic, and I want to talk about like another framework for discussing curve counts. And it's sort of it's based on what I want to call a Grothendieck group of one cycles in complex threefolds. Like all Grothendieck groups, this definition is like sort of tautological. So we have many Grothendieck groups. Grothendieck group of vector bundles on a topological space. Grothendieck group of maybe I can say polygons in R2 or polyhedron R3, etc. Maybe polyhedron in H3. And they all satisfy some tautological universal property. This is the recipient of the universal Euler characteristic on vector bundles. This is the recipient of the universal area functional. I define this as polygons in R2 modulo translation and cutting into 2 polygons. So then there's a theorem that this is equal to R via just the area map. So that theorem then tells you there's no generalized area functional on polygons in R2, and any sort of functional which behaves like area, it's invariant under translation and additive under cutting, is the area, is just the usual notion of area or some scaling thereof. Okay, we know that's not true for R3. So there's the volume functional. There's also this Dane invariant.
So you don't have to impose invariants and rotations.
Oh, sorry, rotations too. Yeah, translations, rotations, and then cutting. Yeah. Yes, this translations, rotating, and cutting also here. Okay, so now for polyhedron R3, there's this other invariant which behaves like volume. It's invariant under rigid motions and additive under scissors congruence, and that's the Dane invariant. And in fact, this is a complete calculation of this group. That's the theorem. But in general, these are like very hard to calculate. So I don't think anyone knows what this group is. You can say what it is in terms of group cohomology, but there's no complete computation. So in general, these are hard to calculate. Okay, so I want to, the definition I'm about to give for one cycles and threefolds is a bit complicated, but I wanted to begin with these simple examples just to explain that it's trying to do something very simple. It's just supposed to be the universal, the recipient of the universal enumerative invariant of cycles of curve counts in threefolds.
Actually, similar to this for computer invariants. I think here you can have classes not only in integral homology but intermediate Jacobian, which countable generate subgroup. Should be more fine.
And would
it's the same here. You consider check classes will have 2 components.
Yes. Okay. Yeah. So I'll have to think whether this applies to that. I'm not sure. Okay. So let's define this Grothendieck group of 1 cycles in threefolds. So let's begin with definition. So Z of X, this is the space, compact 1 cycles in X. So I'll just define it by a picture. 1 cycle is some reduced subscheme of pure dimension 1 with a multiplicity assigned to each of its irreducible components.
So now X is compact?
Not necessarily, which is that's why I wrote compact here. So X is maybe X is just say a complex manifold. Let's say that's Hausdorff.
And you are speaking about a complex one side, that is complex subvariety?
Complex subvariety, yeah. Okay, and it's topologized in the way you expect. So these, a nearby point here, you can have a green chalk on a green board. We'll see how legible that is. So this curve of multiplicity 2 can split into like a double cover that moves off of it. Okay, so this is so in the general setting of like a complex manifold, and it's not algebraic. This is was studied by Barlet space, complex analytic analog of the Chow variety. So all I really will need is its structure as a topological space. But it's nice to know it's an analytic space as a tame topology. Okay. And anytime you have a family, you can do a relative version. So if I have x to b, I guess a submersion, then z of x over b is sort of cycles and fibers. So as a set, it's the union over all the base points. Points in the base of the cycle, space of cycles in the fiber, but not with a disjoint union topology. Right, so with that definition, now I can make the following definition. So I'll call this group compactly supported cohomology of Z over complex threefolds. And it's so we look at all families of threefolds over the simplex xp. Now I'm sort of doing topology here. So delta p really means the real p simplex, but I mean a family of complex threefolds parametrized by the three simplex. So to make that precise, okay, your p simplex is inside Rp, which is inside Cp, and you have a family over some neighborhood in Cp.
So your cycles are not compactible.
Yeah, there's definitely not a proper family.
No.
Yeah, the cycles are compact.
Cycles are compact because in the picture it's not clear. So this X is not compact.
Yeah, the cycles are definitely compact. Yeah, the cycles are compact, but X is not compact. That's important. Yeah. Right. I'll take compactly supported cochains on the space of relative cycles. So this is like some big double complex. It's like a second quadrant complex. Differential goes this way.
So maybe you should tell us more about what the differential is.
Yeah, so the differential is like the internal differential of the compactly supported cochains. That sort of goes up this direction. And then there's the differential, which takes a sum of restricts to the faces. Takes the usual alternating sum, and that's p, and that goes this way.
What is Z?
Z is the space of cycles. It's relative. So x over delta p is a family, and Z of x over p is the space of cycles.
This is the family of of complex cycles. It's analytic in a neighborhood. There are too many of them. I mean, it's not clear how you make sense of it because, like, there are set theoretical. I mean, you can have isomorphic things you don't identify apparently. So then you have too many. I mean, it's not clear what.
Yeah, and okay. So if you want to have this discussion, then okay, you say pick a set of families over. So inductively on P, you pick a set of families over XP, which represents every isomorphism class of such family equipped with a marking of all of its boundary components by stuff in the smaller dimensional simplices you've already chosen. And it's invariant, and you get the same homology group depending on what you choose. Okay, so this looks like sort of a complicated complex, but I want to try to justify the definition in a few different ways. If you have like any map of topological spaces pi from W to B, you can talk about this group, which I'll call compactly supported cohomology of W over B. There doesn't seem to be anyway, this seems to be the existing notation for this. It's just the cohomology of W, compactly supported cohomology of W with coefficients in pi upper star of the dualizing sheaf of B. That's the sheaf-theoretic incantation for this group. And concretely what it is, it's homology of B with coefficients in the fiber-wise compactly supported cohomology. Sort of mixed group, cohomology, compactly supported cohomology in the fibers, but homology in the base direction. And there's like a dual version where you'd consider homology, and yes, that's would be cohomology of W with coefficient of pi upper shriek of the constant sheaf on B, and this is this is cohomology of B with coefficients in the fiber-wise homology, rel infinity, Borel-Moore thing, Borel-Moore homology, dual of compactly supported cohomology. Yeah, so if you imagine that CPX3 is the moduli stack of all non-compact threefolds, and Z over it is this universal space, the universal family of the space of one cycles in the universal family, and apply this definition, this topological object, you get this complex. So that's some sort of systematic origin of this expression. So if you ever tried to sort of figure out what this pi upper shriek operation for a map of topological spaces actually is, then probably you've written down this complex before. That's sort of, the dual of this is exactly this, telling you what pi upper shriek is. Maybe I'll go down. Okay, so another way of motivating this, yes, question. Another way of motivating this definition is to just consider this this bottom edge map right here. So that's just some small part of that complex, but what it looks like is, I guess you'd have sum over all threefolds X of maybe the compact connected components of the space of cycles, there's all family of threefolds over a simplex, one simplex of like this. Now imagine I have a homomorphism out of this group to some target G. Well, that is an enumerative theory of curves, right? Because it tells me for every compact connected component of the space of cycles, space of one cycles, gives me an element of my group, so the count of that, the curves in those classes. And if this composition is 0, that's telling me that this curve count map is invariant under deformation. It says that for every one parameter family of threefolds and every compact connected component of the space of cycles, maybe just take all the cycles, say that's compact. Then the invariant associated to the two endpoints, those are the same.
So I have a couple of very stupid questions, maybe because I don't understand compactly supported cohomology. So first, if it's cohomology, shouldn't this be something that maps from cycles to whatever coefficients you're using? I mean, are you actually counting cycles or the dual of that?
Let's see. So this thing, so this is like the free abelian group on like the compact connected components of this. So to give a map out of this, I just have to tell you for each compact connected component what's its thing. And the reason why is the reason compactly supported cohomology is the right thing to do is that that's what you would pair with the virtual fundamental class. And the virtual fundamental class of m bar of x, this would maps to an element of homology rel infinity of the space of cycles. So any class in this group I can pair against this and get a curve count, a Gromov-Witten invariance curve.
And the other follow-up. The effect of compactly supported is if I have a non-rigid curve in a non-compact X and they can escape to infinity, then it will automatically be counted as zero, basically.
No, it's not appear.
Yes, yeah. We're not able to count it.
We're not able to count it.
Yes. Okay. So if you understand this this picture, then this big complex is simply saying, well, there's no reason to stop at one simplices. I can consider families over any any simplex at all, and that's telling me that sort of this notion of curve count is sort of invariant up to higher homotopy for all arbitrary families. And they're also replacing just H0C with H star C says I can put conditions, intersection conditions on the curves that I count. And that's all. I'll also get counts for those. Okay, so this is a fine definition, but sort of useless unless you can actually compute the group. So that's what the theorem is. So we can't actually compute this group. We need to make a restriction. So I'll just state the theorem and then make a definition. So we look at only the semi-Fano cycles, and now this is the free polynomial algebra on generators X, G, M, K with, let's see, G is genus, M is multiplicity, so it's at least 1, and K is the Chern number, which is at least 0, since it's semi-Fano, but there's a restriction, which is that either M equals 1 or K equals 0. Those are the generators. And these sort of, right, they correspond to cycles of degree M on a local curve, where C is sort of genus G, and the first Chern class of the total space of E paired with the zero section is K. Yeah, so roughly speaking, they correspond to counting, exactly this, counting cycles of degree M on this local curve with the.
It will be automatically compact.
Yeah, so with the C star equivariance, it's. Sorry?
The C star equivariance wasn't present in formalism before.
Yeah, that's so. I mean, right. So, yeah. So there's also the equivariant invariants are somehow a special case of family invariants for the Borel construction. So you can somehow cook up a class in this group which somehow gives you the equivariant count for this geometric setup. C star equivariantly counting these cycles. Okay, so the semi-Fano cycles So cycle is a sum of curves with multiplicity. And it's called semifano when each of the CIs have non-negative Chern number. So that's stronger than saying Z itself has non-negative Chern number. It's not. It's an open condition, but it's not a closed condition.
For the tangent bundle of X itself, you mean?
Yeah. Yeah. The reason is that this controls the dimension of this the space of curves.
Okay, so this is an open, Zariski open in, well, the complement of an analytic subvariety.
Yeah. Let's see. Okay, so and the corollary of this is that this MNOP correspondence holds for semifano, in particular Calabi-Yau, with so-called primary insertions. So I have no idea how to say anything about descendant insertions or remove this semifano assumption.
But in Calabi-Yau case, you don't do any insertions, right?
Yes, so yeah, Calabi-Yau.
So in Calabi case, it's
I mean,
What did you write after semifano varieties
Primary insertions.
yeah, primary insertions. So I didn't say anything about insertions, but there's more complicated conditions you can count.
Yeah, but at least for Calabi-Yau, it's
I mean, okay, yeah, you could consider a family of Calabi-Yaus and then try to insert things, I guess. But yes, for fixed Calabi-Yaus, it's covered by this statement. Yeah. Okay, so the first thing to say about the proof of the theorem is that it's very much inspired by this work of Ionel and Parker on this Gopa-Kurmavafa integrality conjecture. So remember at the very beginning there's this change of variables relating a generating function with rational coefficients to a generating function with integral coefficients, and so that they give you some integrality statement on the Gromov-Witten invariants, and that's called the Gopa-Kurmavafa integrality conjecture, or it's equivalent to it, and so this is a theorem now of Ionel and Parker for Calabi-Yau threefolds. Gopa-Kurmavafa. These are the authors who conjecture this integrality statement for Gromov-Witten theory. So they proved that they proved the statement. But if you read their paper, you realize they don't actually prove this. They prove something much better, which is that they prove that enumerative invariants of Calabi-Yau, of symplectic Calabi-Yau threefolds, are just determined by what they do on local curves. And then, Gopa-Kurmavafa is known for local curves, so it follows. And this theorem is just, well, it's the analog of that in the complex analytic setting. And we have to generalize to the complex analytic setting in order to access this Donaldson-Thomas and Pandharipande-Thomas invariant. So those don't exist in the symplectic setting, as far as we know. Okay, and the complex analytic setting is also much more rigid. So there's a great deal of flexibility in symplectic topology, which is.
You use things which are algebraic in the examples, but so do you need all complex space manifolds, or you need things which are sufficiently algebraic for this?
So the proof uses analytic theories, arbitrary analytic submersions. Now, could you do this with algebraic varieties and prove the same thing. It's possible. I don't know, but you'd have to mess around with the étale topology much more than I'm competent to do. So you'll see in the proof where we need to, and where I'm going to use the fact that we're using the analytic topology, and maybe you can tell me whether we can do the same thing in the étale topology.
But for the corollary, you don't need the DT invariants that are defined for analytic spaces, don't you?
Oh, we do need that. Yeah. I mean, so using the étale topology would allow us to not need DT for analytic spaces. Okay, let's see. Okay, so let's talk about the ideas of the proof of the theorem. Okay, so the first thing, well-known fact, I'll write as a lemma, of generic, almost complex structures on symplectic manifold. Well, it doesn't even need to be symplectic, just any manifold at all. Make all simple curves, meaning not multiply covered, regular. Also known as transverse or unobstructed. So the deformation problem is unobstructed, the moduli space is smooth for a generic almost complex structure. Now, this is not true, and so that's not the basis of this proof. And it's not true at all in the algebraic setting. If I have a compact Calabi-Yau, maybe it's H1 of Tx, which is 0 or something. So there's just no deformations at all. And at the very least, it's always finite dimensional. So this has no hope of working in the analytic setting as stated. But here's what we need to make.
What is simple curves here?
Just a map which doesn't factor through a covering map of Riemann surfaces, a ramified covering. So it's not like covered with multiplicity. So it can have singularities, or it needs to have some point where it's in the immersion on the image.
You mean simple holomorphic curves?
Yeah, everything is pseudo-holomorphic curves. Okay, so lemma is for complex structures, generic comp. This is for anything.
No condition of first Chern class.
Sorry. No, yeah, this is for anything. The condition on the first Chern class comes when you want to say something about multiple covers in terms of the statement for simple curves. Sorry? Transverse. It's the same thing as regular, same thing as unobstructed. There's many words for the same thing. So generic almost complex structures on a neighborhood of a curve in X. Make it regular. So here's X. Here's a curve, and a generic almost complex structure on this neighborhood makes C regular.
No, but it is not necessarily holomorphic for the perturbation.
Yeah. Okay. So make all curves. So make anything nearby C. Anything close to C regular. Okay, it's a slight lie when I say generic. What I mean is there's a very precise sort of perturbation that I'm going to take. And the perturbation is the following. You take a divisor, which is transverse to the curve, and you take a neighborhood, and you express this neighborhood as the gluing of the neighborhood of the divisor and the complement of the divisor over the punctured neighborhood, and you reglue via some vector field, the flow of some meromorphic vector field on this neighborhood of D, poles along D. And using that regluing, you get enough complex structures to make C regular. Okay, so this is a...
Sorry, John, but these are among things that keep C being a complex curve, right?
No, I don't want to worry about whether C stays analytic. It's I just well, this was Ofer's question about this.
But it could be that there is no nearby complex analytic curve.
Then, and we're happy with that. Then they're all regular if they're none of them. That's okay. I don't care about keeping the curves. I just want all the ones that are there to be regular. Yeah. So the fact that this is everything is regular here by doing this perturbation. This is some higher dimensional analog of this familiar fact, which I learned from Maxime at lunch at IHS a long time ago, which is that if you take a Riemann surface and you pick a point and you take a disk and you take a vector field along here, which blows up possibly at that point, and you then that gives you a deformation of the complex structure on the Riemann surface, and you can explore the entire local moduli space of Riemann surfaces by taking these deformations. Okay, so let's see how to leverage this genericity result to prove this. Now, I should remark that because we have such a strong genericity result for strong transversality result in the almost complex setting, the result, the work of Ionel and Parker, they didn't need to consider this big complex. They just needed to consider what amounts to this mapping cone of the first two terms up here. They just needed one parameter families. They didn't need n parameter families. But we have to work with n parameter families, and the reason is exactly because this weaker version of transversality here, it only allows us to get regularity sort of locally on the space of curves, space of cycles. You can't get regularity for all the cycles at once, just neighborhood of one particular cycle. Okay. Yeah. So let's just consider the class of a single of, say, X and maybe just all cycles in class beta in this group. So X is like a projective Calabi-Yau threefold. Okay, I'm going to show you how to decompose this class into a sum of local curves. And, well, okay, then you can do the same thing for any class, but let's just consider the simplest situation to get a handle on the idea. Okay, so the first thing to do, so this is a curve counting problem. We're counting curves in X in this class. The first thing to do is introduce a family. So this is equivalent to I take the trivial family of curves. So I'm going to count curves. I'm counting curves in fibers of this family. Now, that enumerative problem now has dimension n. This one had dimension 0. This one now has dimension n more because I have n parameters. And to compensate for that, we just cop with the projection map pullback of Poincare dual of 0. So that just adds one constraint of, okay, we added all this family, but actually, oh wait, now we're only interested in curves in the fiber over 0. So this does nothing. It's the same enumerative problem. Okay, but now I'm going to take advantage of this extra room, and and we're going to, so we're going to choose an embedding, just any topological embedding. I don't care if it's constructible or anything, just any embedding from the space of cycles on X into Rn. Okay, this is where n needs to be arbitrarily large. I mean, this is some, okay, maybe you only take the ones in homology class beta. So that's compact, it embeds into some Rn. So and n could have to be arbitrarily large to be able to do this. So that's why I need arbitrarily high dimensional simplices in this group. So then this is also equivalent. So this class is equivalent to this same family. But now I take, I guess, pi minus I upper star of Poincare dual of 0. So pi and pi minus I are homotopic. It's an obvious way. And this linearly. So the pullbacks are the same cohomology classes, the same enumerative invariant. But now what you notice about this is that this cohomology class, right, so these are, maybe I should say where these live. These live in the cohomology compact support of, I guess, z of x times Rn. So you're taking the fundamental class of, the virtual fundamental cycle of some moduli space of curves times Rn and pairing it with these.
Do you have to fix the genus of the curve to be compact or moduli space or not?
Yeah, you fix this Euler characteristic. Yeah. Let's see what I want to say. Yeah, it's okay. No, I don't. So, right. So this is the difference between z of x and this m prime of x. So z of x, to make it compact, I just fix the homology class. For this m prime of x or pt of x or something, I need to fix the homology class and the Euler characteristic. So what map, the sum of that map is not proper. The map for a moduli space of stable maps to the cycles is not proper. So to push forward the fundamental class, I need to introduce these like Laurent series coefficients.
Okay. For the space of cycle, beta is enough for the okay. Because you don't have okay.
All right, now the upshot here is that the support of this cohomology class now maps injectively to the base. So concretely, that just means that I have a family of threefolds, and the curves I want to count, there's at most one curve in each fiber. And then I can apply this lemma to perturb the fibers. Now we have enumerative problem for some class. C is this class here in cohomology. So for each, so you have a family of threefolds, and at each point in the base, there's at most one curve that we care about. So now it's just a matter of picking up the pieces. You can take your family, and you can throw away most of it. You can just throw away everything except a small neighborhood of these cycles in K. And now in each fiber, you threw away most of the threefold. All you have is a small neighborhood of the cycle. And then you can apply this lemma to make a generic perturbation. Everything is transverse. So all your curves are isolated, transversely cut out. And Yeah. So there's a tricky lemma, which if there's anything wrong with this this proof, it's in the proof of this lemma, and the lemma states that when you're in this situation, we can always choose these divisors di over some open sets inside B. I don't say open cover, just open sets, such that all curves in K intersect some di. And you can't just do it by general position, because if you do it by general position, you'll realize that these di's, so they have to be disjoint. That's the key. That's the hard part. If you just do it by disjoint general position, you'll realize that the divisors will intersect generically over like a bad part of B, which is codimension 2. So then you have to do some induction on the dimension of B.
It seems to remain me a little bit when I thought long time ago about how to define virtual fundamental class. You locally, using these devices, can represent these things as intersection of two submanifolds, and then to make it see globally, one needs something like this.
Again, the DIs are just like local pieces of divisors of the neighborhood.
Yeah. So I've already cut down X to be just a neighborhood of the curve. Yeah. So you can forget about the divisor and just choose points on C. That's maybe a better way of thinking about it. Choose points on C. And then you see, right, choose a bunch of generic points on C in the family, in codimension 2, they will intersect with each other. And that's bad, because if you have two divisors which go through each other, I don't know how to make this regluing on both at the same time. Anyway, I think the lemma works, and maybe this is a good time to stop.
Questions?
So for this corollary, you have to do DT theory on arbitrary complex manifolds?
Yes, that's right. I think it should be a thing. I need to look more carefully about this.
But that's in the literature, is it? Somebody's done.
I don't know whether it's in the literature. Yeah.
Right. Well, if there's no, maybe further questions can be done over lunch. Let's thank